In the last lecture, we talked about the inverse Z transform in terms of an integral, and that integral is also a special integral. It is a contour integral because the variable is a complex one, Z, which is r e to the power j omega. So, you have to choose a contour and then carry out the integration. If you have to evaluate the integral, then Cauchy's residue theorem can be used, but fortunately for us, for LTI systems of importance, the given Z transform is a rational function, and therefore we can evaluate the inverse Z transform by either partial fraction expansion and then invert term by term, or by long division. The disadvantage of long division is that you may not be able to guess a formula, a general formula for the inverse Z transform. On the other hand, partial fraction expansion always gives you a closed form formula. I also pointed out that if the rational function is Pz by Qz, with the degree of Pz greater than the degree of Q, then this will be written as some polynomial in Z inverse plus a proper rational function P1, where the degree of P1 is less than the degree of Q. That is a proper rational function. Then you invert AZ term by term, which is very easy. If you have a term like 5 z to the minus 5, then its inversion is 5 delta of n minus 5. Agreed? So, this is very easy. For this you have to carry out the partial fraction expansion. I also pointed out that if there are multiple poles, if there are multiple zeros of Q of Z, then you have to in general carry out differentiation, but the differentiation can be avoided by using a simple trick that I had asked you to do, that is, write a set of linear equations by putting specific values of Z and then evaluate the required constants. We pointed out the importance of the region of convergence ROC, and we showed that u of n and u of minus n minus 1 both have a Z transform 1 minus Z inverse. The ROC for u of n is mod Z greater than 1, and the ROC for u of minus n minus 1 is mod Z less than 1. We also took an example in which there were 3 possible ROCs and therefore 3 different sequences. The Z transform is a 1-to-1 transformation only if the ROC is specified, otherwise the answer can be non-unique. We started with the properties of the Z transform, and before that I had introduced some notations, that is, for capital G of Z, if the ROC is denoted by Rg, and for capital H of Z, if the ROC is denoted by Rh, Rg is a symbol for an inequality, Rg1 less than equal to mod Z less than equal to Rg2. Then we also use the notation 1 by Rg, in which 1 by Rg2 less than equal to mod Z less than equal to 1 by Rg1, and then also the meaning of Rg Rh, that is Rg1 Rh1 less than equal to mod Z less than equal to Rg2 Rh2. In these statements I have made a wrong statement. Do you realize where I not less than equal to may infringe upon a forbidden region, that is a pole, and therefore it is strictly less than. Okay. And then we talked about the transforms of several variations, several modifications of G. Firstly, G star of n, the transform was capital G star of Z star. Okay. Then if we have the region of convergence is the same as that of Rg, because mod Z star is the same as mod Z. Then G of minus n was G of 1 by Z, and the region of convergence is 1 over Rg. Then alpha G of n plus beta H of n, the Z transform was alpha G of Z plus beta H of Z, and the ROC includes the intersection of Rg and Rh, but it can be wider. Includes this, can be wider. And I explained why it can be wider, because there can be cancellations, zeros in poles, there can be cancellations of terms also. One may contain negative of one of the terms in G of Z. And then if I shift a sequence by n0, the corresponding Z transform is Z to the minus n0 capital G of Z, and the region of convergence is Rg except for either Z equal to 0 or Z equal to infinity, depending on n0 and depending on cancellations. Suppose your n0 is 1 and there is a term in the denominator which is Z inverse, they may cancel, and therefore it is Rg with the possible exception of Z equal to 0 or Z equal to infinity. In a similar manner, if I multiply the sequence by alpha to the n, then this is G of Z by alpha, and the region of convergence is mod alpha times Rg. Okay. The next property is that of differentiation. That is, if you multiply a sequence by n, then the corresponding Z transform is minus Z dg of Z with respect to Z, not Z inverse. You have to carry out this differentiation, and this will give you a clue for inversion of 1 by 1 minus alpha Z inverse to the power, let us say, R. That is the case of multiple poles. Okay. We shall carry out an example at a little later time. If we have a linear convolution of two sequences G of n and H of n, the corresponding Z transform is the product of the two, and the region of convergence now, well, what is the region of convergence here? I didn't mention this. Multiplication of a sequence by n. It would be the same as that of Rg with possible exception of Z equal to 0 or Z equal to infinity, because there is a multiplication by Z. On the other hand, in this case, the region of convergence would be Rg intersection Rh, but can be wider because there can be cancellation. So, it includes this, can be wider. And finally, the modulation property, that is, if you multiply G of n by H of n, the corresponding Z transform is a contour integral, and it is a convolution in the Z domain. the corresponding Z transform is 1 by 2 pi j contour integral over some contour C g of v, some dummy variable, h of z by v, v inverse dv. This is the formula for modulation, and I strongly urge you to prove each of these columns in the table. The proof of this, for example, is extremely easy if you go from right side to left side. That is, you take this and find the inverse transform of this. It should be easy for you to find out. The clue is that you replace g of v by its equivalent expression, that is summation gn v to summation v to the power minus n, and then interchange the summation and the integration. You should be able to prove it. We will take a very simple example of application. Pardon me? The ROC, yes. Very good question. What is the ROC? Obviously, the ROC has to be the product, it is the product RGRH. ROC is the product RGRH in the sense that we have defined it, but again it includes this. It can be wider than this because there can be cancellations. So, it includes RGRH, but it can be wider. As a simple example of application of this table, let us consider we know what the transform of r to the n sine of n omega 0 multiplied by u of n is. Now, if I want to calculate this ab initio, then we write this as r to the n half e to the j 1 by 2 j r to the n r e to the power j n omega 0 plus e to the power minus j n omega 0. That is correct, minus. All right. So, its Z transform would be 1 over 2 j u n, correct, 1 over 2 j summation n equal to 0 to infinity r to the power n e to the power j n omega 0 well, z to the minus n minus summation r to the power n e to the minus j n omega 0 z to the minus n, n equal to 0 to infinity. We can calculate this ab initio. We can also view, we can sum this up, this is how we have done earlier. We can also view these two sequences, that is r to the n e to the j n omega 0 and r to the n e to the minus j n omega 0 as complex conjugates of each other. In other words, we could write this as 1 over 2 j some sequence v of n, where v of n is r to the n e to the j n omega 0 u n and minus v star of n, right, because here the only change is e to the minus j n omega 0. R to the power n is a real quantity, and if we apply the formula, then my desired transform, let us say x of z, would be 1 over 2 j v of n leads to capital V of z minus capital V star star of z star. Let us see what this is. 1 over 2j Vz is the transform of r to the power n e to the j n omega 0. So, it is 1 by 1 minus r e to the j omega 0, then z to the power minus 1 minus the complex conjugate of this with z also conjugated. So, let us write first what happens if we conjugate the z, r e to the j omega 0 z star inverse, then the whole thing will be starred. Okay. Now, what is this quantity? Obviously, this is 1 by 1 minus r z star star to the power minus 1 is z to the minus 1, and star of e to the j omega 0 is simply r e to the minus j omega 0. Now, you can add the two quantities and get the desired result. What is the result? That algebra you can carry out. The result is r cosine omega 0 z inverse divided by 1 minus twice r cosine omega 0 z inverse plus r squared z to the minus 2 sine cosine delta n un e to the j n omega 0. You should be able to write without consulting the table. Okay? Just like your name and your father's name, you have to remember this. You don't have to turn the pages of the book to find this out. If it is cosine, then what is the modification needed? 1 minus r cosine omega 0 z inverse. Okay. Is it sine or cosine? Thank you. I thought you were allowing me to pass with a mistake. R sine omega 0 z inverse. Now, let us take an example of multiple pole and illustrate how we carry out the actual calculations. My capital X of z is given as z to the power 4 divided by z minus 0.5 whole squared, z minus 0.2 and z plus 0.6. The ROC must be specified. In this case, it is specified as mod z greater than 0.6, which means that it will be a right-sided sequence, a causal sequence. Okay. So, the first thing that we do is a matter of discipline. We write this as a rational function in z inverse. That is, we divide by z to the power 4, then we get 1 divided by 1 minus 0.5 z inverse. Why do we do this? Because we know the inverse transform of 1 by 1 minus alpha z inverse. Okay. Whole squared 1 minus 0.2 z inverse 1 plus 0.6 z inverse, and then we write this as, let us say, a by 1 plus 0.6 z inverse plus b by 1 minus 0.2 z inverse, these are single poles, plus c by 1 minus 0.5 z inverse, plus there will be another term d by 1 minus 0.5 z inverse whole squared, and it is this d that creates a problem. Capital A is 1 plus 0.6 z inverse multiplied by this with 0.6 z inverse equal to minus 1. Similarly, you can find capital B, and C is the problem, D is not the problem. D you can calculate by multiplying both sides by this and putting 0.5 z inverse equal to 1. Okay. I have done this and the results are as follows. Capital A, please do verify this, I do not vouchsafe for their accuracy, divided by 121. B is 1 by 9. D is, D also you can calculate, D in my case it comes to 25 divided by 33. There is a reason why I have kept them as fractions. I have told you the reason. The reason is that we do not truncate unless it is absolutely essential, because in implementation we have to truncate anyway. We have to make because of finite number we cannot represent every number exactly. So, do not truncate till it is absolutely essential. We keep it in this form. Now, the question of finding C. If you notice this expression, the previous expression, what would be a convenient value of Z? To write, I have to write only one equation, there is only one unknown, one equation. Convenient value of Z obviously would be Z inverse equal to 0, that is Z equal to infinity. What would be capital X of Z at infinity? From the given expression it is 1. Therefore, 1 would be equal to A plus B plus C plus D. You see, it is as simple as that. You do not have to differentiate. Okay. So, I get 1 equal to capital X of infinity. Please be careful, the argument is not Z inverse, it is Z. So, Z equal to infinity, it is equal to A plus B plus C plus D, and we know A, B and D, therefore, C is 1 minus the sum of these three, and unfortunately this number comes big, but nothing to worry, you keep it as it is, 116, that is my calculation, divided by 1089. Nothing cancels, I have tried out, nothing cancels, there is no common factors. If there are common factors, do cancel them, make it as simple as possible. Now, the problem is that of inversion. Now, we have found out all of the constants. So, inverse of this would be minus 0.6 to the power n un plus 0.2 to the power n un plus 0.5 to the power n un. Now, only remains this. For this, let us look at this 1 by 1 minus alpha Z inverse. Okay. If I multiply this by n alpha to the n un, the Z transform will be minus Z d dz of 1 by 1 minus alpha Z inverse. This quantity right hand side is equal to minus Z. Now, if I differentiate with respect to Z, first is there will be a minus sign, minus 1 by 1 minus alpha Z inverse whole squared, then the differentiation of the denominator with respect to Z, and therefore, I shall get minus alpha differentiation of Z inverse, which would be minus Z to the minus 2. Take care of all these minus signs, and the result is the result is alpha Z inverse divided by, I hope I am right, 1 minus alpha Z inverse whole squared. What we want is that the numerator should be 1. Therefore, first thing I do is to divide by alpha, So, I get n alpha to the n minus 1 u of n, this alpha goes. Then if Z inverse has to go, then the sequence here should be advanced by one sample, and therefore, I get something interesting I want you to notice, 1 minus alpha Z inverse whole squared, this would be n plus 1, instead of n I shall have n plus 1. If the multiplier was z, then I would have had n minus 1, agreed. So, n plus 1 alpha to the n, then u of n plus 1, agreed. Alpha to the n, because I had alpha to the n minus 1. You see, in the right hand side I had an alpha which I had brought to the left hand side. Okay. Now, this sequence at n equal to minus 1, u of n plus 1 starts at n equal to minus 1, but at n equal to minus 1 the multiplier is 0, and therefore, you can write this as n plus 1 alpha to the n u of n, agreed. So, the whole thing can be written in terms of u of n, alright. You can now collate the final result, and the expression that I get is the following. The final result x of n is equal to, now I truncate 0.2231 minus 0.6 to the power n. I have gone up to 4th place. You should go as many places as your calculator or computer allows. 1111 0.2 to the power n minus 0.0918 0.5 to the power n plus 0.7576 n plus 1. This is that multiple pole term, n plus 1, 0.5 to the n, and the whole thing is multiplied by u of n. This is the simplest possible form. Okay? Right. We go back to the modulation theorem, that is, if g of n is multiplied by h of n, then it is 1 by 2 pi j contour integral g of z h of z of v h of z by v inverse dv. Now, the z transform of this is this quantity. So, I can write summation gn hn z to the minus n. This is by definition the z transform, n going from minus infinity to plus infinity. This should be equal to 1 over 2 pi j multiplied by this integral. Okay. In this expression, if I make g of n equal to h of n, let g of n equal to h of n and small z equal to 1, then the left hand side simply becomes the energy of the sequence, that is g squared n, energy of the sequence, and the right hand side becomes 1 over 2 pi j contour integral over c. Put z equal to 1, then you get g v, capital H of V inverse, but capital H is the same as capital G, multiplied by V inverse dV. Since V is a dummy variable, we can as well change it to Z, right. So, I can write this as H of Z, or let us take G of Z, G of Z inverse dz. Agreed? Now, if the region of convergence includes the unit circle, then we know the Fourier transform exists. In other words, the contour C can be the unit circle if ft of g of n exists, then we could replace small z by e to the power j omega. Agreed? Is this point clear? If the ROC includes the unit circle, then we can as well replace C by the unit circle. Agreed? And on the unit circle, small z is equal to e to the j omega. And it does not take long to show that the right hand side integral, one more point before I go to the integral. One of the sufficient conditions for the existence of Fourier transform is that g of n is absolutely summable. So, if g of n is absolutely summable, or in general if the Fourier transform exists, then my summation g squared n should be equal to 1 over 2 pi, j disappears, because if we are on the unit circle, then our only variable is omega. Small r is equal to 1, and therefore minus pi to plus pi. That is all. We go round the circle, we go from minus pi to plus pi, and then we get g of e to the j omega multiplied by g of e to the minus j omega, which is its complex conjugate, and therefore we get magnitude g of e to the j omega squared. Then z inverse dz simply becomes d omega. All right. If you put z equal to e to the j omega and differentiate, this is the result. And so we have proven Parseval's relation. Okay. Parseval's relation is a consequence of the modulation theorem of Z transform. It has to be. However, I must caution you that there are sequences for which Fourier transform exists, but Z transform does not, and vice versa. If the Fourier transform does not exist, then we cannot apply this theorem. However, we can apply the general modulation theorem in Z transform. Okay?
So, left hand side, does that imply energy? Because modulus is not there.
Oh, small g we took as a real sequence. Otherwise, we will have to take Gn, we will have to, okay, good point, good point. You see, we took here g of n equal to Hn. If g of n was complex, then we would have taken Hn equal to g star of n, and the same result would have followed. Okay, very good point. I appreciate it. Now, we now go to, we have so far talked about signals. How do they interact now with systems? That is, we take a discrete time system and see how it can be characterized in the transform domain. We have learnt about Fourier transform, DFT and Z transform of signals. How do they help in characterizing discrete time systems? Well, one of the things that you should appreciate is that any signal, be it analog or discrete time, any signal can be decomposed into sinusoids. When you take Fourier transform, when you take a periodic signal in the continuous time domain, we take Fourier series, which is a summation of sinusoids of frequencies which are harmonically related, that there is a fundamental frequency that is 1 divided by the period, then its second harmonic, third harmonic, fourth harmonic, and so on and so forth. When you go to when the signal is not periodic, then what do? We take Fourier transform, which means that the spectrum consists of all frequencies, a continuum of frequencies, not just the fundamental and its harmonics. There is no fundamental for a non-periodic signal. The fundamental frequency is For a non-periodic signal, a signal which exists only from, let us say, minus capital T to plus capital T, what is the fundamental period? 0. And therefore, starting from 0 we go up to infinity, all frequencies exist. But it can also be looked upon as a continuum of sinusoids, and therefore any signal, be it continuous time or discrete time, can be thought of as superposition of sinusoids. Any discrete time signal can be thought of as a superposition of sinusoids. The separation between two adjacent sinusoids may be infinitesimally small, d omega. That is why we use that integral. Okay? And you also know that any sinusoid can be written as a sum of two exponential signals. By Euler's theorem, any sinusoid can be represented as a sum of two exponential signals. Therefore, an exponential signal is the most elementary signal as far as characterization of a system is concerned. If we know the response to a sinusoid or an exponential signal, then we know the response to all other signals. Okay? So, we try to find out the response to an exponential signal, and for that we specialize our system to LTI, linear time invariant system, for which you know that the output is given by the convolution of the input and the impulse response, x of n minus k multiplied by h of k. I should have written it the other way around, but does not matter. N k goes from minus infinity to plus infinity. Now, if to this system we apply an input x of n equal to e to the power j omega n, then the corresponding output, you put here x of n minus k equal to e to the power j omega n minus k, then the e to the j omega n term can be taken outside the summation, because the variable of summation is k. So, I get the output as e to the power j omega n multiplied by summation h k e to the power minus j omega k, k going from minus infinity to plus infinity. And you notice that since this term is independent of n, it can be simply replaced by a constant h of e to the j omega, constant independent of n. All right. So, y of n is a constant h of e to the j omega multiplied by e to the j omega n. Such functions which, when supplied as an input to the system, produces an output which is a constant multiplied by the same function, are called eigenfunctions. So, e to the j omega n is an eigenfunction of a linear discrete time invariant system, e to the j omega n. And you notice that this capital H of e to the j omega, let me write it down, capital H of e to the j omega multiplied by e to the j omega n. You notice that capital H of e to the j omega is the summation of h k e to the minus j omega k, k going from minus infinity to plus infinity, is simply the Fourier transform of h of n. All right. And this quantity capital H of e to the j omega is known as the frequency response of the system. The the quantity capital H of e to the j omega is a characteristic of the system, just as h of n is the characteristic of the system. It is the same characterization transformed to the time domain. It is called frequency response because it involves omega. All right. It shows the complete frequency behavior of the system, and in general you see this will be a complex quantity. It can be written as h of e to the j omega can be written as magnitude h of e to the j omega multiplied by e to the power j angle of h of e to the j omega, and magnitude must be a real quantity, real and even. Similarly, the phase is odd. Is it real? Phase must also be a real quantity. Agreed? So, angle and phase are equivalent terms. Now, it is interesting to see that e to the j n omega, if it leads to capital H of e to the j omega, e to the j omega n, because the system is linear, if we take the real parts of both sides, they should correspond to each other. In other words, cosine of n omega, if we know the response to e to the j n omega, then we know the response to cosine n omega also. It will be real part of this, which means that capital H of e to the j omega, then cosine of omega n plus angle of h of e to the j omega. All right, that's all that it matters. Capital H can be written as magnitude times e to the j angle h, which adds to j omega n, and therefore the real part becomes cosine of this. And in a similar manner, if I have an input of sine n omega, then all that differs is instead of cosine I get a sine, and these give the steady state response of the system to either a exponential signal or a cosine signal or a sine signal. So, this signal is the most important signal in practice. Okay. In the time domain, what is the most important signal? Delta n. Because if you know h of n, then you know the total characteristic of the system. Correspondingly, in the frequency domain, it is e to the j n omega. If you know the response to e to the j n omega, or you know h of e to the j omega. So, they are equivalent characterizations. Okay. Let us take an example. The example that we take is the m point moving average system. We have taken this example earlier also, that the output at an instant n is the average of all x of n starting from the present instant to the m minus 1th instant, k equal to 0 to m minus 1. What kind of a system is this? Is it FIR or IIR? Impulse response. FIR, because h of n is nothing but 1 by m summation delta n minus k, k equal to 0 to m minus 1, which I can write as 1 by m for n between 0 and m minus 1, and it is 0 otherwise. So, it is indeed an FIR system, and its frequency response. For frequency response, all we have to do is to take the Fourier transform of this. So, we shall get a summation 1 plus e to the minus j omega plus e to the minus j omega up to the mth term, that is e to the minus j omega m minus 1, the whole thing divided by m, 1 by m. So, the frequency response capital H of e to the j omega, let me write it again, 1 by m, 1 plus e to the minus j omega plus etc. up to e to the minus j m minus 1 omega. And since this is a geometric series, we can sum it up, 1 over m 1 minus e to the minus j omega m divided by 1 minus e to the minus j omega. And you know that this can be written in terms of sines, and it can be written as 1 over m sine of omega m divided by 2 divided by sine of omega by 2, then e to the power minus j omega m minus 1 divided by 2. Is that okay? I am taking e to the minus j omega m by 2 out and e to the minus j omega by 2 out. So, the angle becomes e to the minus j omega m, and since e to the minus j omega by 2 is in the denominator, it comes as a positive sign here. Is this result correct? It is very tempting to identify this as the magnitude and this as the phase, which is not correct, because sine omega m by 2 by sine omega by 2 changes signs. Okay? Whenever it changes sign, the phase changes by 180 degrees. For example, if I plot sine of omega m by 2 divided by sine of omega by 2 versus omega, then the omega equal to 0 value is, at omega equal to 0, it is 0 by 0 form. So, you apply L'Hopital and get the result as capital M. Result will be capital M. Omega by 2, this is M. One differentiation will bring M, and then it decreases. It goes like this.
So there is an omega term in the coefficient.
Omega term in the
Coefficient 1 by, I'm sorry, m term in the coefficient 1 by m. So m and m will cancel out.
say it again.
It is 1 by m into some sine term divided by another sine term.
Oh, wonderful. So, therefore, I shall have it as 1. What he says is the following, and he is quite correct. There is a 1 by m here. So, he is correct and incorrect both. Only when I write this as 1 by m, the maximum will be 1. Okay, we will take this as 1, all right. 1 by m times this. Then it executes damped oscillations, that is, it goes like this and then like this and so on. Now, up to this point, where does the first 0 occur? When the angle becomes equal to pi, that is, this would be 2 pi by m. Omega equal to 2 pi by m will make this equal to pi, that is the first 0. Omega equal to 2 pi by m, the denominator remains non-zero. Then this angle would be 4 pi by m, and so on. At every such transition, the phase shall change by pi. So, the magnitude is not this, but you have to take its magnitude. Okay? The magnitude of capital H is equal to 1 over m magnitude of this quantity, sine of omega m by 2 divided by sine of omega by 2, and that quantity obviously this negative halves will flip over. So, the magnitude plot shall be like this. Okay? And therefore, the magnitude and phase of the frequency response can be written like this: h of e to the j omega magnitude is equal to 1 over m, as I had written earlier, sine of omega m by 2 divided by sine of omega by 2. This is the magnitude. And the angle of capital H is equal to, if you take help of the previous expression, I have the expression here. You see, the angle would be omega m minus 1 by 2 minus negative, okay? Then you have to take care of the phase transitions by pi. Wherever there is a zero crossing, there occurs a phase transition. So an angle pi is added there, and therefore the general expression becomes minus omega m minus 1 by 2 plus, there are many transitions. Let us see how many we shall add later, but at each transition a step function of magnitude pi, a phase of pi is added to the whole thing. So step function of magnitude pi, it occurs at omega minus 2 pi by m multiplied by k, where k goes from 0 to, how many such transitions shall occur? Our range of vision is omega equal to 0 to pi, and therefore sine omega m by 2, when it becomes pi, then the transition stops. But m by 2 may or may not be an integer. So where would the last transition occur? At the integer closest to m by 2 but less than m by 2. For example, if capital M was 5, then the last transition shall occur at 2, not 2.5. Okay? So we indicate this by m by 2 and a special sign. The sign is this, not the square bracket, the upper end is truncated. This indicates m by 2, this indicates integer closest to m by 2 but less than m by 2. Similarly, if I write a quantity n like this, then integer closest to n but greater than it. And if I close both, then it is equal. That is at the integer value of n. Now here it is m by 2, and I have got a plot here of the magnitude as well as phase for two values of capital M. One is capital M equal to 5 and the other is 14. You see, when capital M equal to 5, then the first transition occurs at what value of omega? 2 pi by 5, okay, and 2 by 5 is 0.4. The ordinate here, axis here is omega by pi, x axis. So it occurs at 0.4. The next one shall occur at 0.8. There are only two transitions here, because 5 by 2 is 2.5 and the integer closest to it is 2. The next one is pi at 1. There is no more transition. Okay? And look at the phase. The phase starts from 0, goes up to the value minus omega 5 minus 1 by 2. How much is there? Okay, 2. And this transition then occurs at 0.4. At 0.4, this height is exactly equal to 180 degrees. It goes up by 180. Now then it remains the quantity sin omega m by 2 by sin omega 2 remains negative. For how long? When it remains negative, the phase is controlled by that term minus omega m minus 1 by 2. So, it comes down again. These two lines are parallel. Then at the next transition 0.8 again another pi is added. So, the phase becomes a triangular waveform with a rising tendency. Okay? The phase is not minus omega m minus 1 by 2. You have to state the phase within the range of vision. Okay? Is this point clear? If capital M is 14, then you see the transition occurs at less than 0.2. What is 14? How many transitions now? Exactly 7. 14 by 2 is 7. So, 1, 2, 3, 4, 5, 6, 7, and the seventh one is the end of the vision at omega equal to pi. Okay? So, the phase behaves in a very peculiar manner, and in specifying magnitude we have no ambiguity. In specifying phase, the transition must be taken care of. It is not phase